For over 60 years, we've been told the same thing. Humans will walk on Mars in about 20 years. That was the promise in 1970. It was the promise in 2000. And somehow, it's still the promise today. The date never seems to arrive. So let me ask you a simple question. What is actually stopping us? The honest answer is uncomfortable. It's not because we stopped trying. It's not because we ran out of money or dreams. Something real is standing in the way, something most people have never stopped to think about. Tonight, I'll walk you through exactly what stands between humanity and Mars, step by step, until you understand why it's so much harder than it looks. Now get yourself comfortable, hit subscribe, we begin. For 60 years, we have been 20 years away from Mars. Think about that for a moment. A child born the year we first promised to send humans to the red planet would be old enough now to hold grandchildren, and still, no human boot has ever pressed into Martian soil. The date always sits just past the horizon, always close enough to believe in, never close enough to touch. And here is the strange part. It was never for lack of wanting. Since the 1960s, Mars has been fixed in our imagination as the obvious next step, the second planet, the backup, the frontier waiting patiently for us to grow up and arrive. Today, that pull has never been stronger. The United States, China, and a handful of other nations are all reaching toward it at once. And alongside them stands something new in history, a single private company, SpaceX, that now launches more rockets than most countries on Earth. The man behind that company, Elon Musk, frames it in the starkest terms imaginable. To him, this is not exploration. It is insurance. A second home for the human species, so that if something ever goes catastrophically wrong on this one, our only world, the story of humanity does not simply end. A backup drive for a civilization that currently exists in exactly one fragile copy. So, the will is there, the money is there, the genius is there, and yet we remain here. To understand why, look first at the record of what we have already sent, not the people, but the machines. Mars is where spacecraft go to die. Across the decades, we have flung dozens of probes, landers, and orbiters at that small red dot, and roughly half of them never made it. They burned up, went silent, missed the planet entirely, or slammed into the surface as fresh craters. Engineers have a grim nickname for this pattern. They speak of a kind of curse hanging over the red planet, as if Mars itself were guarding the door. There is no curse, of course. There is only difficulty, layered, stacked, and relentless. Because here is the truth that 60 years of failure keeps trying to teach us. The thing standing between humanity and Mars was never ambition, and it was never talent. It is a specific stack of interlocking problems, each one hard enough to stop a civilization on its own, and each one hiding another problem directly beneath it. Solve the one on top, and the next rises to meet you. Solve that, and a third is already waiting. Let's start with the very first wall, the one you hit before you have even left home, the journey itself. We tend to picture space travel as a straight line, point the ship at Mars and go. But you cannot aim at Mars, because by the time you arrive, Mars will no longer be where you aimed. Earth completes one lap around the Sun every 365 days. 1 year, the rhythm your entire life is built on. Mars is slower and farther out, and it takes 687 days to finish a single loop, nearly 2 of our years for one of its own. Picture 2 runners on a circular track, one on an inner lane, one on the outer. The inner runner, Earth, moves faster and keeps lapping the outer one, which means the 2 planets are almost never in the right position relative to each other. Most of the time, they are on opposite sides of the same enormous stadium, and the distance between them does not just change, it swings violently. At their closest possible approach, Earth and Mars come within about 34 million miles of each other, roughly 55 million kilometers. That already sounds impossibly far, so let's make it real. That distance is about 140 times farther than the Moon. Every crewed mission in human history, all the way back to Apollo, has stayed within that single moon's distance of home. Mars, at its very friendliest, sits 140 of those journeys away. That is the good day. On the bad day, when the two planets drift to opposite sides of the Sun, the gap stretches to around 250 million miles, roughly 400 million kilometers, more than 1,000 times the distance to the Moon. The same destination, the same red planet, but now more than 7 times farther than its closest approach, simply because of where each world happens to be in its orbit. This is why you cannot leave for Mars whenever you like. The two planets only swing into the right alignment, close enough and angled correctly for a fuel-efficient crossing, once about every 26 months. Every 2 years and 2 months, a door quietly opens in the sky. It stays open for a few weeks. Then it closes. Miss it, and the consequences are brutal. You either wait more than 2 full years for the next window, watching the planets drift apart and back again, or you attempt to force the trip out of alignment, which demands a quantity of fuel that ranges from wildly impractical to flatly impossible. Think about what that means for a real mission. You cannot be a month late, you cannot slip your schedule. The universe hands you a narrow gap on its timetable, not yours. And if your rocket is not ready, the sky simply shuts. One of those windows is opening at the end of this very year, and what happens with that window tells you almost everything about how hard this really is. For years, the most optimistic voice in all of spaceflight aimed straight at it. SpaceX's Starship, the most powerful rocket ever built, flying test flights right now, climbing, straining, and sometimes breaking apart, was meant to send an uncrewed ship through that gap at the end of this year, carrying no people yet, just cargo and machines. A first attempt to prove the crossing could even be survived. Musk himself once gave that window 50-50 odds, a coin flip, and the single hardest obstacle, he admitted, was something almost no one outside the field ever thinks about: the ability to refuel a spacecraft in orbit before it can even begin the long fall toward Mars. But that coin has already landed on delay. Early this year, the company quietly pushed its Mars plans back by years, turning first toward the Moon, partly to chase a lunar landing it is contracted to deliver, and partly because that very refueling still is not ready. The first real attempt at Mars has slipped to the next window, 2 years away, and perhaps well beyond it. The rocket, for all its power, has still never gone, and that should tell you how steep this first wall really is. When even the boldest plan on Earth quietly bends to the difficulty is real. So how do we even attempt the crossing? Not by pointing and firing, by throwing an enormous, patient curve. The standard path to Mars is called a Hohmann transfer, named for the German engineer who worked it out on paper a full century ago, long before any rocket could fly it. The idea is elegant, and once you see it, you cannot unsee it. Instead of driving straight at the target, the ship gives itself one great push near Earth, and then shuts its engines almost entirely off, coasting along a long, curving elliptical arc that swings halfway around the Sun before finally meeting Mars on the far side. You are not aiming at where Mars is. You are aiming at where Mars will be, months from now, when your arc and its orbit finally cross. It is exactly what a quarterback does throwing a long pass. You never throw the ball to where the receiver stands. You throw it to the empty patch of field where he is going to be, and you trust the two paths to meet. Now stretch that single throw across 100 million miles and 8 silent months, with one chance to release and no way to adjust in flight. Get the timing wrong, and the ball sails through empty space forever. The engines are off for almost the entire journey. And that is not a design choice. That is a confession about fuel. Here we reach the deepest law beneath all of it. The reason the engines must stay cold, the reason the ship must coast, the reason every plan for Mars is squeezed before it even begins. More than a century ago, a nearly deaf Russian schoolteacher named Konstantin Tsiolkovsky, working alone, wrote down the equation that still governs every rocket ever built. And that equation contains a trap so severe that engineers speak of it the way sailors once spoke of the sea, with respect and a little fear. Here is the trap in plain terms. To make a rocket go faster, you must burn more fuel. But that fuel has weight, and to lift that extra weight, you need still more fuel. And that fuel, too, has weight, demanding yet more fuel beneath it. The relationship is not gentle and additive, it is exponential. It runs away from you. Imagine packing for a road trip so long that the gasoline itself becomes the heaviest thing in the car. So heavy that you must bring extra gas just to move the gas, and then extra again to move that. Very quickly, the car is almost entirely fuel, hauling a tiny sliver of actual passengers and supplies. That is every rocket on the launch pad. Overwhelmingly fuel, carrying the barest thread of everything you actually wanted to send. This is why chemical rockets, the only kind we have ever flown, place a hard ceiling on how much mass can go to Mars. And that single ceiling reaches its cold fingers into every part of the mission. Less mass means less food, less shielding, less water, less air. Every kilogram you spend on one need is a kilogram stolen from another. The rocket equation does not just make the journey hard, it forces a chain of painful compromises down through every problem still to come. Solve the trajectory, in other words, and you have not won. You have only reached the second wall. Now sit with the crossing itself. Once that great push is spent and the ship falls into its silent arc, the crew faces something no human has truly endured. 7 to 9 months of coasting through open space, depending on the path. Not orbiting a friendly planet, not circling home, falling through the dark between two worlds, with radiation streaming through the emptiness around them. There are no pit stops. There is no service station, no waypoint, no safe harbor to limp toward. Once the ship commits to that arc, there is no turning back. The fuel to reverse course simply does not exist. They are committed the way a diver is committed the instant they leave the board. And here the honest doubt arrives. Surely you might think, we already know humans can survive that long in space. We have kept people up there for a year and more. We have. Just once, and it is worth knowing his name. A Russian cosmonaut and physician named Valery Polyakov holds a record that has stood, unbroken, for more than 30 years. In the 1990s, he stayed aboard the Mir space station for 437 days straight, nearly 14 and a half months, circling Earth more than 7,000 times. He did it deliberately as a doctor to answer one question with his own body. Could a human being survive long enough to reach Mars and come home? When he finally landed, his first words were essentially that we can fly to Mars. No one has beaten his record since. The closest anyone has come in all the years since was still just over 2 months short. So the endurance is real, but there is a catch buried inside that triumph, and it changes everything. Every one of those record-breaking missions, including Polyakov's, took place in low Earth orbit, just a few hundred miles up, close enough to look down and watch storms cross the oceans of home. And that closeness was a lifeline the whole time, even if no one felt it. If something had gone wrong, a fresh capsule of supplies could be launched within days. If a crew member had fallen gravely ill, an escape craft was always docked and waiting to bring them home in hours. And doctors on the ground could talk to them in real time. A normal, flowing conversation, question and answer, help arriving the instant it was needed. A Mars crew loses every single one of those safety nets at once. No resupply. When the food runs low, nothing is coming. No evacuation. There is no lifeboat back to Earth from halfway across the solar system, and no real-time doctor, because the very laws of physics forbid it. When they are at their farthest, a single message crawling at the speed of light takes as long as 22 minutes to reach Earth, and another 22 to return. Ask a question in a crisis, and your answer arrives, at best, 3/4 of an hour later, long after the crisis has already decided the outcome. No one is coming. That is the sentence that hangs over the entire journey, and this is only the first wall, the one made of distance, timing, and fuel. Behind it, others are already rising. There is what those silent months of weightlessness quietly do to the human body, draining the bone, thinning the blood, reshaping the heart itself in ways we are only beginning to measure. There is the invisible radiation that the shielding cannot fully stop, a second threat that no wall of metal can simply block. There is the landing, a descent so violent and so fast that for 7 terrible minutes, no human on Earth can help, no matter how badly they want to. There is the silence, those messages arriving too late to matter. There is the raw problem of survival on arrival, a crew that must somehow pull air, water, and rocket fuel out of a frozen, poisoned, long-dead planet. And there is the mind, years sealed inside a metal can, staring at the same few faces with no door to step through and no sky to walk beneath. Here is what makes Mars so uniquely, staggeringly hard. You cannot solve just one of these. They are not separate puzzles waiting in a line. They are knotted together, each one tightening the others. Solve the trajectory, and life support becomes the wall that stops you. Solve life support, and radiation is still standing there, patient, waiting its turn. Every answer you find spends resources that another problem desperately needed, because the rocket equation is always in the room, always counting every kilogram. This is why 60 years of the brightest minds our species has ever produced have not gotten us there. Not one wall, every wall, all at once, with no one coming to help. Mars is very likely the hardest single thing humanity has ever attempted. 8 walls stand between us and that red soil, and every one of them is taller than it looks from here. We have just seen the first, the wall of getting there. The next one is far stranger and far more personal, because even if the ship holds, even if the trajectory is perfect and the landing survivable, there remains a problem the engineers cannot rivet or weld or fuel their way past. A problem we carry inside our own skin. The human body, it turns out, was never built for this, and the moment it leaves Earth, it quietly begins to come apart. The moment the engines fall silent and the ship begins to coast, something quiet and relentless starts happening inside every person on board. Not because anything is broken, because everything is working exactly as it was designed to, just for the wrong world. Your body runs on a single ancient assumption: gravity. Every day of your life, your skeleton has been pushing back against the weight of your own body, and that constant strain is the only reason your bones stay strong. The rule is brutally simple. Use it or lose it. Take the weight away, and your body does something that feels almost like betrayal. It begins to dismantle the very bones it no longer thinks it needs. Researchers first watched this happen back in the 1970s aboard America's Skylab station, and the pattern has held ever since. In the weightlessness of space, the load-bearing bones, the spine, the hips, the long bones of the legs, lose somewhere between 1% and 2% of their mineral density every single month. Let that number settle, because it sounds small until you anchor it. Here on Earth, a woman past menopause, at genuine medical risk of osteoporosis, might lose 1% to 2% of her bone density in a whole year. An astronaut loses that same amount in a single month. A 6-month mission can strip as much bone from the skeleton as a full year of one of the fastest bone loss conditions we treat on the ground. And by some measures, it outpaces severe osteoporosis by more than tenfold. A perfectly healthy person can age their hip by a decade in half a year. And here is the part that should stop you cold. Some of them never fully get it back. Years after landing, certain astronauts still have not returned to the bone density they launched with. The body, once it starts unbuilding, does not always know how to build again. Now think about what that means for Mars. A crew coasts for months, their skeletons quietly thinning the entire way, and then they arrive, weakened, at the one moment the whole mission demands the most from their bodies, stepping out onto a new world. In a heavy suit, on legs that have been dissolving since they left home. That is the trap. The journey weakens them precisely for the arrival, and bone is only the beginning. Muscle goes the same way, and faster. In space, your muscles no longer fight anything. Standing, walking, simply holding yourself upright, all of it vanishes, and unused muscle wastes away. Astronauts fight this with a punishing routine, strapping themselves to treadmills and resistance machines for about 2 hours every single day, more than almost any athlete on Earth trains. 2 hours, daily, just to slow the decay. And even that is not enough to stop it completely. It is like bailing water from a boat with a small leak. You can keep up, but the water never stops coming in. Then there is the one muscle you cannot afford to lose, the heart. Your heart has spent your entire life pumping blood upward against gravity, and that steady labour is part of what gives it its familiar elongated shape. Take the gravity away, and the heart simply stops working as hard. In a study of 12 astronauts, doctors trained them to scan their own hearts with ultrasound before, during, and after their missions. The results were unsettling. In space, the heart drifted toward a rounder form, becoming, on average, about 9% more spherical. Think of a muscle you stop exercising, softening and losing its defined shape. The heart does something eerily similar. It relaxes into a shape it was never meant to hold, and no one yet fully understands what years of that would do to it. All of this, the thinning bone, the wasting muscle, the reshaping heart, happens before a single boot ever touches Martian soil. But the strangest thing gravity was quietly doing for you all these years was managing your own fluids. On Earth, gravity constantly pulls the blood and water in your body down toward your feet. In space, that pull vanishes, and all that fluid floods upward into the chest and the head. Astronauts feel it immediately. Their faces puff up and round out. Their legs grow thin and spindly. They describe a permanent, low-grade head cold, a stuffy, congested pressure that never quite lifts. Crews have a grimly affectionate name for the look: puffy face, bird legs. It would almost be comic if it stopped there. It does not. That rising tide of fluid raises the pressure inside the skull, and that pressure pushes directly on the back of the eyes. Over the months, it can swell the optic nerve, flatten the back of the eyeball from a sphere into something slightly squashed, and blur an astronaut's vision, sometimes permanently. Doctors have a name for this now: spaceflight-associated neuroocular syndrome, and it is common. In surveys, around 60% of astronauts on long-duration missions report some loss of visual sharpness, more than double the rate seen on short flights. Sit with what that means on the way to Mars. The people we send will have to repair failing machinery with their hands, read instruments to navigate, and, if it comes to it, perform emergency surgery on each other, with no help arriving for months. And the very journey there may be slowly stealing the one sense all of that depends on: their eyesight. And while the body reshapes itself, its oldest defense quietly stands down. The stress of spaceflight, the confinement, the broken sleep, the surge of stress hormones like cortisol, suppresses the immune system. The body's guards grow sluggish and stop patrolling as carefully, and in that lowered guard, something ancient stirs. Most of us carry dormant viruses inside us for our entire lives. The herpes family, the viruses behind cold sores, behind chicken pox and shingles, behind mono. After the first infection, they never truly leave. They hide, silent, held in check by a healthy immune system for decades. In space, that leash slips. NASA researchers found that more than half of astronauts, around 53% on shorter flights and 61% on longer station missions, began shedding these reawakened viruses in their saliva and urine. The immune cells that normally hunt them down stayed weakened not just during the flight, but for up to 2 months after landing. Most crews felt nothing, but the longer the mission, the more the viruses stirred, and a mission to Mars would be longer than any before it. None of this, remember, involves anything going wrong. This is the body performing exactly as evolution built it, for a planet it has now left behind. And we have not yet talked about the thing coming from outside, because the body is not only unbuilding itself from within, it is also being quietly shot through particle by particle from without. Here on the surface of Earth, you live at the bottom of 2 invisible shields you have never once thought about. A thick blanket of atmosphere overhead, and a vast magnetic field generated deep in the planet's molten core that wraps the entire world and deflects the constant storm of radiation streaming in from space. You have been sheltered your whole life, and you never felt it. A ship crossing to Mars leaves both of those shields behind, and out in that open dark, the crew faces 2 entirely different kinds of radiation. 2 enemies, each dangerous in its own separate way. Let's take the sudden one first. The sun does not burn at a steady, gentle rate. Every so often it erupts, hurling out a violent blast of high-energy particles in what scientists call a solar storm. If one of these blasts catches a crew in open space, unshielded, the dose can climb high enough, fast enough, to cause acute radiation sickness, the kind that makes a person violently ill within hours, and in a severe enough case, could kill. And here is what makes it so frightening. These storms give almost no warning. Not days, not even reliable hours. Sometimes only minutes stand between the first sign of an eruption and the wave of particles washing over the ship. There is no outrunning it. The only defense is to have already built a heavily shielded shelter inside the craft, and to reach it in time, every single time for the entire journey. That is the sudden threat. The other one never stops at all. Streaming constantly through all of space are galactic cosmic rays, the shredded remains of exploded stars, flung across the galaxy for millions of years. Most are simple, fast-moving particles, but a fraction of them are something far worse, the nuclei of heavy atoms like iron, moving at nearly the speed of light. And these heavy nuclei carry so much energy that they do the one thing ordinary radiation cannot. They punch straight through metal, through the hull, through the shielding, through a human body like a bullet passing through fog. Here is the cruel twist, the part that feels almost unfair. When you try to stop these particles with a thick wall of shielding, they can slam into it and shatter, spraying out a shower of smaller secondary particles on the other side. The very wall built to protect the crew can end up spraying them with fresh radiation from the inside. Add too little shielding, and it fails. Add too much of the wrong kind, and it can make things worse. So how much radiation are we actually talking about? For a long time, that was a guess, until we sent something to measure it. When NASA sent the Curiosity rover to Mars, it carried a small radiation detector, quietly recording the dose the entire way across, and then on the surface. For the first time, we had real numbers instead of models. The verdict was sobering. During the cruise alone, the instrument absorbed the equivalent of a full-body medical CT scan roughly every 5 or 6 days, over and over for the whole crossing. Add up a realistic mission, the trip out, a long stay on the surface, and the trip home, and the total dose lands at around 1 sievert of radiation. To feel that, you need a yardstick. NASA now sets a single career limit for every astronaut, about 0.6 of a sievert, across their entire working life. That ceiling already represents more than 2 centuries worth of the ordinary background radiation you soak up standing on the ground. And a single trip to Mars would deliver roughly a full sievert, nearly double what an astronaut is permitted to absorb in an entire career, spent in one journey. A dose of 1 sievert is associated with something like a 5% rise in the lifetime risk of dying from cancer. One mission, a career's worth of radiation, and then some, all at once. But here the story becomes less certain than it first appears, and honesty demands we slow down. Not everyone agrees on how dangerous that number truly is. On one side stand NASA's models, which err deliberately toward caution, treating every particle of radiation as carrying some proportional risk, with no completely safe dose. On the other side stand critics, among the loudest, the aerospace engineer Robert Zubrin, a lifelong champion of sending humans to Mars. Zubrin argues the cancer fears are badly overstated. He points out that some of the alarming models lean on animal experiments, where mice were blasted with radiation at dose rates far higher than any astronaut would ever face, and he questions whether those results mean much for a real crew. The deeper uncertainty is genuine, and it sits at the heart of the science. The standard way we estimate low-dose radiation harm assumes a straight line. Half the dose, half the risk, all the way down to 0. But no one is fully certain that line holds at the low, slow, steady exposures of deep space. It may overstate the danger, it may not. We have never had a group of humans out there long enough to know for sure. This is not a debate to be settled with a clever line. It is a real and open question, and the people we send will, in a sense, become the experiment that answers it. And cancer, strangely, may not even be the worst of it, because those heavy iron nuclei do not only threaten the body, they may threaten the mind. When one of those particles tears through the brain, it can carve a microscopic path of destruction directly through living neurons, the cells that carry every thought you have ever had. In animal studies, researchers have exposed mice and rats to this kind of radiation and then tested them, and some have come back showing impaired memory, slower learning, and poorer decision-making, with visible damage to the delicate wiring between brain cells. Now, we have to be careful here, because the science is genuinely unsettled. When researchers moved from blasting animals with a single type of particle to simulating the true messy mix of deep space radiation, some of those effects came out milder than feared, and a few studies showed no clear harm at all. The real risk to the human brain remains honestly unknown, but consider what is at stake if even part of it is true. A crew, alone, hundreds of millions of miles from any help, facing constant life or death decisions, and the very radiation they cannot escape may be quietly eroding the judgment those decisions depend on. On a mission with no backup, a dulled mind is its own kind of catastrophe. So what can we actually do about any of this? The best answer we have is almost primal. Hide underground. The most promising plan is to bury the habitats, to pile meters of Martian soil, called regolith, over the top of them, letting the sheer mass of rock and dirt soak up the radiation the way it does on Earth. Some scientists look hopefully at Mars's lava tubes, vast natural tunnels carved by ancient volcanic flows that could shelter an entire base beneath solid rock. But those tubes are a promise, not a plan. We have spotted them from orbit, but no one has ever been inside one. We do not know if they are stable or on the verge of collapse. We do not know what hazards wait in that darkness. They may be humanity's first Martian home, or a trap we cannot yet see. And even if we solve all of it, the bones, the blood, the eyes, the radiation, one enormous unknown remains. And it may be the most fundamental of them all. Everything you have heard so far describes what happens in zero gravity, in the weightlessness of the crossing, but Mars is not weightless. Mars pulls with about 38% of Earth's gravity, a little more than a third. A person who weighs 150 pounds here, around 68 kilograms, would weigh only about 57 pounds standing on Mars. Not nothing, but not home either, somewhere strange in between. And here we arrive at what may be the most quietly terrifying blank in the entire endeavour. We have decades of data on what zero gravity does to the body. We have a lifetime of data on what one full Earth gravity does. But between those two numbers, between 0 and 1, we have almost nothing. Scientists call it the gravity gap. No human has ever lived in partial gravity long enough for us to measure what it does. So the single most important question for anyone hoping to actually live on Mars has no answer. Is 38% of Earth's gravity enough to keep bones strong, hearts firm, and eyes clear? Or will a body on Mars keep slowly falling apart, just more gently than in the void? We do not know. We have never tested it, not once. And the question grows heavier still when you follow it to its natural end. No mammal, not one, has ever been conceived, carried through pregnancy, and born in space, let alone in the fractional gravity of another world. Whether a human child could even develop properly in a Martian womb, whether its bones and heart could form correctly under a third of Earth's pull, whether it could ever grow strong enough to one day stand on Earth, every last piece of it is a total unknown, a blank page. For a colony, that is not a footnote. That is the whole question of whether it has a future at all. But all of this, the fragile body, the untested gravity, the unknown child, assumes the crew even makes it to the surface alive. And that assumption hides the next wall entirely. Because before anyone can worry about living on Mars, they first have to survive arriving there. And the arrival is a fall, a violent, fiery plunge through a thin and treacherous sky, compressed into about 7 minutes. 7 minutes in which everything must go perfectly. 7 minutes in which no one on Earth, no matter how brilliant, can do a single thing to help. To understand why, we have to talk about those 7 minutes, and about a silence that stretches across the solar system. So, picture the moment of arrival, not as a gentle docking, but as a fall. After months of silent coasting, the ship reaches Mars not slowly but screaming in at more than 12,000 miles an hour, around 20,000 kilometers an hour, fast enough to cross the entire United States, coast to coast, in about 12 minutes. And now it has to stop. On a world that offers almost nothing to stop it with. Here is the cruel paradox at the heart of landing on Mars, and it traps every engineer who has ever faced it. Mars has an atmosphere, but it is a trickster. The air there is less than 1% as thick as the air you are breathing right now, more than 100 times thinner than Earth's. To feel how thin that is, climb in your mind to the very edge of space above Earth, around 100,000 feet, 3 times higher than a passenger jet ever flies, where the sky has already gone black. The air at the surface of Mars is roughly as thin as that, and that thinness is a trap that cuts both ways. The atmosphere is just thick enough to be dangerous. Slam into it at 12,000 miles an hour, and the friction alone builds a wall of heat fierce enough to incinerate an unprotected craft. The leading heat shield glowing at temperatures over 2,300 degrees Fahrenheit, hot enough to soften steel. So, it will burn you. But then, in the same breath, that same atmosphere is far too thin to actually slow you down enough to land safely. Thick enough to set you on fire, too thin to catch you. That is the wall no one can talk their way around. For decades, we have beaten this problem, but only by cheating and only with small, light robots. Every spacecraft we have ever landed on Mars used the atmosphere as a brake, a technique engineers call aerobraking. The craft hides behind a heat shield and lets the thin air bleed off its speed, trading velocity for heat. Then, once slowed enough, it pops a parachute to shed the rest. The Viking landers pioneered this back in 1976, and every mission since has leaned on the same basic recipe. And it works, beautifully, right up until the moment you try to land something heavy. Because parachutes on Mars are fighting that same thin air. With so few air molecules to push against, a parachute simply cannot grab enough to slow a large mass. Engineers have pushed this method about as far as it can physically go. And where did it top out? At roughly 1 metric ton. That is not an abstract number. 1 metric ton is the weight of Curiosity and of its twin Perseverance, each about the size of a small car. The heaviest machines humanity has ever set down on Mars weigh about as much as the vehicle sitting in your driveway. And that is the ceiling. Past that, the parachutes fail. The physics runs out. Now hold that ceiling in your mind, because what we need to land next shatters it completely. A robot the size of a car is one thing. A crew of living human beings is something else entirely, and everything they need to survive has to come down with them. Think about what a crewed landing actually has to carry to the surface, all at once, in a single vehicle. The habitat they will live in, the life support machinery that makes their air, months, even years, of food, a chemical plant to manufacture the fuel for the trip home, and the crew themselves. Stack all of that together, and estimates for a crewed Mars lander start at around 20 metric tons, and climb, in many plans, toward 50, even 100. Let that land. 100 metric tons is roughly the weight of a full-grown blue whale, the largest animal that has ever lived. We are talking about setting a blue whale down, softly, on a target, on another planet, when the heaviest thing we have ever managed is the weight of a small car, and no system on Earth or off it has ever landed anything close to that mass on Mars. Not once, not in a test. The gap between what we have done and what we need to do is not a step, it is a chasm. So if parachutes are out, what is left? The only answer anyone has is to stop relying on the air at all, and instead fight the fall with raw thrust, to fire powerful rocket engines downward against the descent, slowing the vehicle by brute force the entire way to the ground. A propulsive landing. This is the entire idea behind SpaceX's Starship, the towering vehicle we met at the very beginning of this journey. Starship is built from the ground up around this single bet. It carries no giant parachutes for the final descent. Instead, it plans to scream into the Martian atmosphere, use its own body to bleed off the worst of the speed, and then light its Raptor engines and ride them down to a controlled touchdown, balancing on a pillar of fire like a pencil landing on its tip. The physics of this is sound. On paper, it works. But here is the distance between paper and reality, and it is enormous. Doing this reliably, automatically with zero human input, after the machine has endured 9 months in deep space, freezing and radiation battered, and must then perform flawlessly on the first and only try, that has never been proven, not even close. And Starship's own recent history shows exactly how brutal the challenge is. Across 2025, SpaceX flew a series of test flights, and several of the early ones ended the same way, the vehicle breaking apart, tumbling, erupting into fire over the ocean. The company clawed its way to later successes, but the message of those failures is honest and clear. Landing a giant rocket precisely under power is one of the hardest things anyone has ever tried to engineer. and they are still trying. Now compress this entire violent, unforgiving sequence into the time it takes to brew a pot of coffee. From the instant the ship touches the top of the atmosphere to the moment it either rests safely on the surface or does not, only about 7 minutes pass. NASA's own engineers, who have lived through this again and again with their robots, gave it a name that is not marketing. They call it the 7 minutes of terror. For a moment, imagine you are strapped inside. The vehicle bucks and shudders as it bites into the thin air. Outside your window, the heat shield flares white hot, and a sheath of glowing plasma wraps the craft, blotting out the stars. The deceleration crushes you into your seat. The ground is rushing up faster than any human has ever fallen toward another world. Somewhere in the final moments, the engines must light, exactly on time, and swing the whole falling tower upright to settle it down gently. Every step must fire in perfect sequence, perfect timing, perfect choreography, and if any single one fails, there is no second attempt. And through all 7 of those minutes, here is the part that turns the terror cold. No one on Earth can help you. No one, in fact, even knows it is happening. To understand why, we have to talk about the one limit in this entire story that no engineering, no money, and no genius can ever overcome. The speed of light itself. Radio signals, every command, every warning, every cry for help, travel at the speed of light. And the speed of light, which feels instant here on Earth, is agonizingly, unbearably slow across the gulf to Mars. Depending on where the 2 planets sit in their orbits, a single signal takes somewhere between 3 and 22 minutes to make the one-way crossing. Send a message and wait for a reply, and the round trip can stretch to as long as 44 minutes. Sit with what that actually means for a human being in trouble. Suppose something goes wrong on that ship, and the crew calls Earth for help. At the worst moment, that plea takes 22 minutes just to arrive. Mission Control hears it, understands it, works the problem, and radios back their answer. And that answer takes another 22 minutes to return. By the time the crew hears a single word of advice, the emergency they radioed about is 3/4 of an hour in the past. Whatever was going to happen has already happened. Light is the fastest thing that exists in the universe, and across this distance, it is still far too slow to save anyone. Now bring those 2 facts together, the 7-minute descent and the 20-minute delay, and you arrive at something almost impossible to accept. When Curiosity landed, Mars was so far away that its radio signals took 14 minutes to reach Earth. The landing itself took 7. Do the arithmetic, and a chilling truth falls out. By the time NASA's engineers on Earth received the very first signal saying the craft had touched the top of the atmosphere, the ship had, in reality, already been sitting on the surface of Mars for around 7 minutes, alive or shattered into wreckage. Either way, it was already over. The entire life or death event had finished before Earth even knew it had begun. The engineers who led those landings describe the feeling with brutal honesty. During those 7 minutes, they say, the team on Earth has exactly as much control over the outcome as a person watching the broadcast at home, which is to say, none at all. They are, in their own words, simply along for the ride. This is not a flaw we can patch. This is not a bug in the software waiting to be fixed. This is a permanent, unbreakable law of every mission to Mars, written into the fabric of physics and there to stay. And that law does not end when the crew lands. It follows them every single day for the entire time they are on Mars. A fire breaks out in the habitat. An airline springs a leak. A crew member collapses with something the others cannot name. In every one of these moments, the people on Mars are alone with the problem in a way no human explorers in history have ever been. There is no one to call who can answer in time. Ground control back on Earth can listen and can offer advice, but their advice arrives minutes too late to matter for anything fast. For any true emergency, the crew and the machines around them must diagnose it, decide, and fix it themselves in real time with no one coming. Which means every critical system on that mission must be understood deeply and completely by the handful of people on board. They cannot phone an expert, they must be the experts. For the engines, the reactor, the medical kit, the air, the water, all of it. And where their own knowledge runs out, they will have to lean more heavily than any crew before them on onboard computers and artificial intelligence, software trusted to catch what the humans miss in the seconds when Earth is a silent point of light in the sky. Their survival, in the end, depends on a terrible kind of self-reliance, and the planet around them is not going to make it any easier, because even the descent has more traps waiting inside it. The Martian air is not just thin, it is treacherous and unpredictable. Great dust storms can rise without much warning, thickening the sky and choking visibility at the worst possible moment. Winds shift in ways that are hard to forecast from millions of miles away. Every one of these can nudge a landing off target, and on a descent where the margin is already razor-thin, a nudge can be fatal. And then there is a silence that comes not from distance, but from the sun itself. Roughly every 26 months, that same rhythm that governs the launch windows, Mars slips behind the sun as seen from Earth in an event called solar conjunction. During that time, for about 2 weeks, the sun's hot, charged outer atmosphere sits directly across the path of every radio signal, scrambling and corrupting anything we try to send. For a couple of those days, Mars vanishes behind the sun's disk entirely, and communication stops altogether. NASA does not even attempt to command its Mars robots during this window. The risk of a garbled instruction is too great. For 2 weeks, every 2 years, the line simply goes dead. Imagine that happening while a crew is fighting for their lives on the surface, and there is nothing anyone can do about it, because it is the sun, and the sun does not negotiate. So where does this leave us? Of all the obstacles standing between humanity and Mars, the landing may be the strangest, because of one quality it has that the others do not. We understand it completely. We can calculate the mass. We can measure the atmosphere. We know to the second how long the fall takes and how long the silence lasts. There is no mystery here, no hidden physics, nothing waiting to be discovered. And yet, understanding it perfectly has not let us solve it. The margin for error in those 7 minutes is, for all practical purposes, 0. And we have never once landed the mass a crew would need. It stands there in full daylight, fully mapped, fully understood, and still, for now, genuinely unclimbed. The most clearly defined and most stubbornly unsolved problem in the entire stack. But suppose for a moment that we solve even this. Suppose the impossible landing goes perfectly. The engines fire, the tower settles, the dust clears, and a crew steps out, alive, onto the red soil. In that triumphant moment, they would face a truth more relentless than anything the journey threw at them. They would be standing on a dead world, a place with no breathable air, no drinkable water, no fuel to get home, no food that will ever grow on its own. Everything the journey tested was about getting there. Now the planet itself asks a colder question. Not whether you can arrive, but whether you can stay. Whether you can pull your very survival, molecule by molecule, out of a frozen and poisonous ground that offers nothing freely. And that is a fight measured not in 7 minutes, but in every single day that follows. So the crew is down, alive, on the surface, on another world, and immediately the planet begins counting what they owe it. Every single day, just to stay alive, one human being needs roughly 2 pounds of food, a little under a kilogram, close to 2 pounds of oxygen to breathe, and several litres of water for drinking alone before a single drop is spent on washing or growing anything. Multiply that across a crew, and across the years a Mars mission demands, and the numbers turn monstrous. NASA's own food scientists estimate that a multi-year trip would require over 7,000 pounds of food, more than 3 metric tons for each crew member. For a crew of 4, that is more than 28,000 pounds of food alone, the weight of a fully loaded delivery truck made of nothing but meals. And here is the wall that stops the obvious solution cold. Just carry it all from Earth. We cannot. To lift a single ton of anything off Earth and set it gently on Mars costs a staggering amount of fuel. And fuel, as we have seen, is the tyrant that devours everything. Fully supplying a crewed mission from Earth, including the propellant to come home, would take something like 400 tons of material, spread across multiple of the largest rockets ever flown. It simply cannot be shipped, which leaves only one path forward. If the crew cannot bring what they need, they must make it, out of Mars itself. Scientists have a name for this: in situ resource utilization. It means using what is already there, and it is not a clever bonus feature. Without it, there is no staying, no return, no colony, ever. So what, on a dead and frozen world, is actually there to use? The answer begins in the one place you would least expect: the thin, poisonous air. Here is the strange gift hidden in the Martian atmosphere. That air is about 95% carbon dioxide, the very gas your own lungs push out as waste. On Earth, it is a trace exhaust. On Mars, it is nearly the entire sky. And carbon dioxide, it turns out, is raw material. Run that carbon dioxide together with hydrogen, add heat and a catalyst, and a chemical reaction discovered over a century ago by the French chemist Paul Sabatier does something almost magical. It produces 2 things at once: methane, which is rocket fuel, and water, from air. Take that water and run an electric current through it, splitting it apart, and you get 2 more prizes: oxygen to breathe, and hydrogen, which you feed right back into the machine to start the cycle again. Air becomes fuel and water becomes oxygen. It is a loop that could, in principle, keep a crew breathing and give them a full tank for the ride home. And this is not a fantasy on a whiteboard. We have already done a piece of it. Aboard the Perseverance rover sits a device the size of a toaster called MOXIE, and between 2021 and 2023, it did something no machine had ever done. It pulled breathable oxygen straight out of the Martian air. At its best, MOXIE made about 12 grams of oxygen per hour, twice what its designers had even hoped for. 12 grams. Hold on to that number because it is the whole problem in miniature. 12 grams an hour is roughly what a small dog breathes. Over its entire mission, MOXIE produced about 120 grams total, a few hours of air for one person. But a full-scale plant, one that could fuel a rocket to carry a crew home, would need to make 2 to 3 kilograms of oxygen every hour. That is around 200 times what MOXIE managed. We have proven the toaster works. Now we have to build the factory, one that runs flawlessly for years on another planet with no one to repair it. And that beautiful loop has a hidden crack in it. It runs on hydrogen, and hydrogen is the one ingredient Mars does not simply hand you. There is almost no free hydrogen in the Martian air. What Mars does have is water ice, locked beneath the surface, frozen into the ground across much of the planet. And inside that ice is the hydrogen we need. But getting it is brutal, industrial work. You have to find the ice, drill into frozen soil as hard as rock, haul it, melt it, and purify it. Because that Martian water is not clean. It is laced with the same toxic salts that poison the whole surface. And every one of those steps, the drilling, the hauling, the melting, the purifying, devours enormous amounts of energy. Which brings us to the thing that quietly governs all of it, the one resource that everything else depends on: power. Think about what dies the instant the power fails on Mars. The machines making oxygen stop, the heaters keeping the crew from freezing go cold, the water recycler halts, the fuel plant shuts down. On Earth, a blackout is an inconvenience. On Mars, a long enough loss of power is simply death, quiet and total. Every other problem on this world bows to this one. No power, no anything. So how do you keep the lights on, 34 million miles from the nearest wall socket? The obvious answer is the sun. Solar panels are simple, proven, and have no moving parts to break. But Mars betrays them in two ways. First, Mars sits much farther from the sun than we do, and receives only around 40% of the sunlight Earth gets. Noon on Mars is dimmer than a grey, overcast afternoon here, so every panel already works at a fraction of its earthly strength. And then there is the dust. Fine, red dust settles constantly onto the panels, slowly smothering them, choking off their power a little more each day. And every so often Mars does something no other planet in the solar system does quite so violently. It throws a dust storm so vast it wraps the entire globe, turning day into a dim red twilight for weeks on end, blocking out more than 99% of the sunlight. We have already watched this kill. NASA's Opportunity rover ran on solar power and was built to last just 90 days. Through luck and stubborn engineering, it survived for nearly 15 years, more than 60 times its designed life. And then, in 2018, one of those planet-swallowing dust storms rolled in, dimmed its sky, and starved it of light. It was not smashed, it was not broken, it simply went dark and never woke up. That is the warning. For a rover, losing power means losing a mission. For a crew whose every breath depends on that power, relying on the sun alone is a bet no one should be willing to make. It is a single point of failure with human lives behind it, which leaves the harder, heavier, more honest solution. Nuclear power. A small fission reactor does not care about dust or storms, or the long Martian night. It produces steady, relentless heat and electricity, month after month, no matter how dark the sky becomes. And we have taken the first real step. In 2018, NASA and its partners ran a test called Krusty, switching on a compact nuclear reactor built for space and proving the concept worked, at a scale of about 1 kilowatt, with the design meant to reach 10. 10 kilowatts is enough to run a handful of ordinary homes, but a crew's life support base would need far more than that. Tens of kilowatts just to keep people breathing and warm, and a true settlement would eventually need hundreds, even thousands. Scaling that little proven reactor up to the size Mars demands has never been built, and flying a nuclear reactor to another planet opens its own tangle of problems. The safety of launching fissile material off Earth, and the careful question of not contaminating Mars itself with our machines. We have lit the match. We have not yet built the furnace, and even with power flowing, the crew still has to eat, for years. So why not simply plant crops in the Martian soil? Because that soil is not soil at all. What covers Mars is regolith, crushed rock and dust, with none of the living richness of Earth's dirt. It holds no organic matter, none of the patient bacteria that pull nitrogen from the air to feed plants. And worse, it is laced throughout with those toxic salts called perchlorates, present across the surface at levels that would poison most crops outright. Here the perchlorate becomes one of the strangest characters in the whole story, because it is both villain and gift. In the human body, it attacks the thyroid. It is genuinely toxic to us. Yet heat that same salt, and it releases oxygen. The very chemical that could poison the crew could also help them breathe. Scientists have not resolved this tension so much as learned to live inside it. A poison and a resource wearing the same face. To grow food safely then, the crew would likely have to abandon the ground entirely, growing plants in water or mist instead, in sealed indoor farms. But those systems demand intense artificial light, and in a habitat buried underground for protection, with no sunlight reaching in at all, every one of those grow lights pulls hard on the same precious power budget that everything else is fighting over. Food, it turns out, is not separate from the energy problem. It is another mouth feeding on it. And then There is the dust itself, not just as a smotherer of solar panels, but as a quiet, invisible threat to the crew's own bodies. Martian dust is nothing like the soft dust in your home. With no rain and no flowing water to ever wear it down, each grain stays fine, jagged and sharp, and carries a static charge that makes it cling to everything. Suits, seals, airlocks, skin. It works its way into every gap. And here is the part that unsettles the doctors most. If that fine, glass-sharp dust is tracked inside and breathed into human lungs, over months and years it may scar them from within, a slow, grinding damage that researchers compare to silicosis, the lung disease that has haunted miners for centuries. The very ground they came to explore may be, with every breath indoors, slowly cutting them apart. So the crew needs shelter, but on Mars, a home is not a comfort. It is a machine for holding back a world that wants them dead. That habitat has to do several impossible things at once. It must hold pressure, so the crew's blood does not boil in the near vacuum outside. It must stay warm against nights that plunge to around 80 degrees below 0 Celsius, about 110 below 0 Fahrenheit, with temperatures that can swing by nearly 100 degrees between afternoon and midnight. And it must shield against the radiation we spoke of before, which never stops falling. Even the air pressure inside becomes a cruel trade-off. Fill the habitat with full Earth-like pressure, and it is comfortable and safe to breathe. But the walls must be thick and heavy to contain it, and heavy is the one thing you cannot afford to land. Lower the pressure to save weight, and the walls can be lighter. But now the air must be richer in oxygen, and an oxygen-rich room is a room that burns fiercely at the smallest spark. Safe but heavy, or light but flammable. There is no free choice, and the best shield against radiation is the planet itself, burying the habitat under thick layers of that same regolith, which means, before the crew ever arrives, robots must go ahead and build, digging, piling, constructing a buried shelter on an alien world, autonomously, with no human hand to guide them. A home waiting underground, cramped and low and dim, that must somehow be livable for years, yet light enough to have been landed in the first place. And inside that buried home, one more law rules everything. Nothing can be wasted. Nothing. On Earth, waste simply goes away, down a drain, out a vent, into a landfill you never think about again. On Mars, there is no away. Every drop of water the crew drinks, every breath of air, every scrap of moisture must be captured, cleaned and used again. On the International Space Station, engineers have pushed water recycling to an astonishing 98%, reclaiming almost every drop of sweat, breath and urine. And even that is not quite enough for Mars, where the tiny 2% lost day after day for years would eventually run a crew dry. The dream is to close the loop completely, to feed the carbon dioxide the crew exhales into that Sabatier machine, turning their own waste breath back into fuel and water, around and around, a perfect circle with nothing lost. On paper, it is elegant. In reality, a fully closed life support system, running for years at the scale a Mars crew needs, has never once been built or proven. Not here, not there, nowhere. And when a crew member finally steps outside that fragile home, onto the surface itself, everything we have described, the pressure, the warmth, the shielding, the clean air, must somehow travel with them, wrapped around a single human body. That is the spacesuit, and calling it a suit undersells it completely. It is a wearable spacecraft, a personal pressure vessel holding back the vacuum, a climate control system fighting those 100-degree swings, a barrier against radiation, against searing ultraviolet light, and against that clinging, toxic dust. All of it, worn like clothing, flexible enough to let someone kneel and dig and build. And its greatest weakness is the most human part of it, the hands. The gloves have to seal in full pressure while still letting fingers feel and grip and work delicate tools. Astronauts have complained about this trade-off for decades. Make the gloves strong enough to hold pressure, and they grow stiff and clumsy. Make them nimble, and they risk failing. Dexterity versus survival, fighting each other at the fingertips. And here is the quiet, sobering truth beneath all of it. The suits we have, the ones on the space station, the ones designed for the moon, are not built for Mars. They cannot handle its gravity, its cold, its light, its dust, all at once, for the years a mission would demand. The suit that a human being could actually live and work in on the surface of Mars does not yet exist. Not as a prototype, not anywhere. It is still just a drawing. So imagine, for a moment, that we solve all of it. The air, the water, the power, the food, the shelter, the suit, every machine of survival, working in perfect concert on a dead world. Even then, the hardest part of the whole endeavor is not any of these things, because sealed inside that suit, inside that buried habitat, at the end of every wire and every machine, is a human mind. And the mind carries something that no reactor can power and no factory can manufacture: its own fragile need to not come apart, alone, confined, and further from home than anyone has ever been. And that may be the most dangerous variable of them all. You can engineer a reactor. You can test a landing 1,000 times in simulation, but you cannot debug a human being. And the human being is the part of this mission most likely to break. Consider what we would actually be asking of a person. Years, not weeks, years, sealed inside a metal can barely larger than a small house, with the same 3 or 4 faces, day after day after day. No stepping outside for fresh air, ever, without first climbing into a suit that could kill you if it failed. And outside that suit, no open sky to walk under, no rain on your skin, no forests, no oceans, no animals, no strangers, not a single living thing on the entire planet, except the handful of people trapped in there with you. And when the loneliness presses in and you reach out to Earth, to family, to anyone, there is no conversation waiting, only a delayed message sent into the silence that will not be answered for the better part of an hour. You cannot talk to home. You can only leave it voicemails across the void. We are not guessing about what this does to people. We have watched it happen. For decades, scientists have studied humans in the closest places Earth has to offer, the environments they call isolated, confined, and extreme. The crews who winter over in Antarctica, submariners sealed beneath the ocean for months, volunteers locked in sealed chambers. These are our windows into what a Mars crew would face, and what they show us is sobering. The clearest window of all sits on a high, frozen plateau in Antarctica, a research base called Concordia, run in part by the European Space Agency, ESA. They have a nickname for it. They call it White Mars, and it earns the name. For much of the year, no aircraft can reach it. From February to November, no one comes in and no one gets out. Winter temperatures fall to around 80 degrees below 0 Celsius, roughly 110 below 0 Fahrenheit. The sun vanishes for months at a stretch. Colour, sound and smell nearly disappear from a white world that stretches empty in every direction. And here is what nearly 2 decades of research there has revealed. The long, dark winters do measurable damage to the mind. Crew members show slowed thinking, poorer spatial reasoning, a harder time judging where things are in space. Mood swings, sleeplessness, and rising tension between people forced together too long. Researchers have even found signs that prolonged isolation can physically shrink parts of the brain, quietly eroding the very tissue we think and remember with. And Concordia, remember, is the easy version. Because everything that makes Concordia hard, Mars makes harder. A winter over crew is larger, a Mars crew would be smaller, just a handful of people with nowhere to retreat when tensions rise. A winter over lasts one dark season. A Mars mission stretches across roughly 3 years. And an Antarctic crew, however isolated, still stands on their home planet, under a sky they recognize, knowing that when spring comes, a plane will land. A Mars crew has none of that certainty, and layered on top of it all is a weight the icebound scientists never carry, the knowledge that a single mistake, any hour of any day, could kill everyone. There is no off-duty on Mars. The life support hums with your life inside it, always. And then there is a psychological blow that no human being in history has ever felt. One we can barely even study because it has never happened. Think about the astronauts who have looked back at our world from orbit. Nearly all of them describe something transcendent, seeing the whole Earth hanging there, blue and alive and whole, a feeling so profound it has a name, the overview effect. It rearranges people, it fills them with awe. Now imagine the opposite. As the ship pulls away toward Mars, Earth does not stay that comforting blue marble. It shrinks. Day by day, week by week, our entire world, every person who has ever lived, every ocean, every memory, draws down smaller and smaller until it is no longer a globe at all, until it is a dot, a single pale point of light, indistinguishable from a star. And then, eventually, even that is gone. Psychologists have a name for this moment they know is coming, the Earth out of view phenomenon. And the honest truth is, we do not know what it will do to a person. No human has ever been unable to find home in the sky. No one has watched the Earth become a fleck of light and then vanish, leaving them truly, cosmically alone. It may be the loneliest thing a human being has ever felt, and a Mars crew would feel it first. There is also a strange pattern that keeps surfacing in these long confinements, one that troubles mission planners deeply. Researchers call it the third quarter phenomenon. Across many isolated missions, in space, in Antarctica, in simulations, morale does not decline steadily the way you might expect. Instead, people often hold together well through the first half, buoyed by novelty and purpose. And then, somewhere past the midpoint, the third quarter of the mission, something sags. The realization sinks in that they are only halfway, with the entire grueling return still ahead, and mood, motivation, and cooperation can all slump at once. Now, honesty demands a caveat here. The evidence for this effect is real, but genuinely mixed. Some studies find it clearly, others barely at all. So scientists still argue over how universal it truly is. But even the possibility matters enormously, because here is the stakes. In a crew that's small, that isolated, with everyone depending on everyone, a single interpersonal breakdown, one feud, one person who stops functioning, one collapse of trust, could cripple the entire mission. And crew conflict, lost motivation and burnout have been documented again and again, even among elite hand-picked, highly trained volunteers who knew exactly what they signed up for. The mind, it turns out, is harder to engineer than the rocket, and the body brings its own emergencies. This is where the gap between what a Mars crew needs and what we can give them splits open most brutally of all: medicine. Think about what happens on Earth when something goes truly wrong inside your body. You call for help, and within minutes an ambulance comes. Within an hour you are in front of a specialist, in a hospital full of equipment and expertise built up over centuries. That entire safety net, the ambulance, the hospital, the surgeon, the evacuation, is the invisible foundation beneath every human life on this planet. On Mars, all of it is gone. No ambulance is coming because there is no ambulance. No evacuation is possible. The same physics that traps them there for the mission traps them there in a crisis. And no specialist can guide their hands in time, because every word of advice from Earth arrives up to 20 minutes too late to matter. All they have is what they carry, their own training, a limited medical kit, and a doctor back on Earth whose voice always arrives from the past. And the conditions that would test this are not exotic. They are ordinary. Here is what haunts the doctors who plan these missions. It is not some rare alien disease. It is the everyday medical emergencies that any of us might face on a normal Tuesday, the ones that are almost trivially survivable here, and could be death sentences there. A burst appendix. On Earth, a routine surgery. You are home in days. On Mars, with no surgeon and no operating room, it can kill. The threat is taken so seriously that in some early space programs, crews actually discussed removing healthy appendixes before flight, cutting out an organ purely so it could never fail at the worst possible moment. Kidney stones are worse still because Mars actively causes them. Remember the bone loss we spoke of, the calcium draining out of the skeleton in low gravity. That calcium floods into the urine, where it can crystallize into stones. In fact, kidney stones are already the second most likely reason a crew member would need to be rushed off the International Space Station in an emergency. On a mission where no such rescue exists, a single stone lodged in the wrong place could become a slow, agonizing catastrophe. Even a dental abscess, an infected tooth, becomes a genuine threat when there is no dentist within 100 million miles and the infection has nowhere to go but deeper. This danger is older than spaceflight. When the Lewis and Clark expedition pushed into the American wilderness in 1804, one man, Sergeant Charles Floyd, died of what was almost certainly a burst appendix, the only member lost on the entire journey. Not because his companions did not care, but because, in that place and time, no one could save him. A Mars crew would be exploring under exactly that ancient shadow, carrying once again the ordinary human body into a place where ordinary help cannot reach. So the crews we send will have to become something more than astronauts. They will carry surgical and critical care skills far beyond basic first aid, trained to cut, to stitch, to keep a dying crewmate alive with their own hands, guided only by delayed instructions and their own nerve. Engineers are racing to help, developing artificial intelligence systems that could diagnose illness on the spot, and robotic tools that might one day let a surgeon on Earth guide an operation from afar, though the delay makes even that agonizingly limited. And beneath all of it lies a quiet, disturbing possibility we touched on earlier. The same radiation streaming through their brains and the same crushing isolation wearing at their minds may be slowly degrading the very judgment those life and death decisions depend on. The doctor and the patient may both be compromised by the same journey, which raises the final and perhaps most important question of the entire endeavour. If the machines can be built and the risks can be mapped, who exactly do you send into this? Crew selection for Mars would be one of the most demanding human filters ever devised. And here is the surprising part, the part that runs against everything the movies have taught us. Technical brilliance is not enough. Of course, the crew must be superb engineers, scientists, doctors, pilots. But decades of research into who thrives in isolated, extreme environments points to something else entirely as the deciding factor. Not raw skill, character. What actually matters is resilience, the ability to keep going when everything in you wants to stop, genuine compatibility with the others, tested over time, not on paper, and above all, a deep, unshowy calm under uncertainty, exhaustion, and fear. The research is strikingly consistent and strikingly unglamorous. The people who do best are not the loud heroes of the story. They are the quietly competent ones, the ones who keep their routines even after the motivation has completely drained away, who make the coffee, run the checklist, and do the work when they no longer feel like it. The ones who manage their own fear and frustration privately without bleeding it onto the crew around them. The truest picture of a Mars crew is not a band of daring adventurers. It is something more like the crew of a ship on a long voyage, or a surgical team in a difficult operation. Small, deeply interdependent, every person's steadiness holding up everyone else's, and the stakes of choosing wrong are total. Get the machines wrong, and you have an engineering failure you might fix. Get the people wrong, and the failure is human, quieter, harder to predict, and impossible to repair from 200 million miles away. So we have walked the full length of it now, the distance and the fuel, the fragile body, the impossible landing, the dead world that gives nothing freely, and the fragile, irreplaceable mind that must endure all of it. And standing at the end of that list, a strange and honest question rises up. After everything, the graveyards of failed missions, the thinning bones, the silence, the loneliness, the ordinary illnesses turn deadly. Why would anyone go at all? What is it about that small red light in the sky that has pulled at us so relentlessly for so long that human beings would willingly face all of this to reach it? To answer that, we have to turn away from the machines and the medicine for a moment and look at Mars itself, not as an engineering problem, but as the object of one of the oldest, strangest, and most haunting obsessions in human history. Because long before it was a destination, Mars was a mirror, and what we have seen in it, and what may still be hiding there, is a story all its own. For almost all of human history, Mars was nothing but a light, a single reddish point, wandering slowly across the night sky, moving in a way the fixed stars never did. And its colour, the colour of dried blood, unsettled the people who watched it. Cultures across the ancient world tied that red wanderer to war, to death, to bad omens. They did not know it was a world. They only knew it moved strangely, and that its colour meant something was wrong. That is the first thing to understand about Mars. Long before it was a place, it was a feeling. A screen onto which we projected our fears. And when we finally built instruments to look closer, we did not stop projecting. We simply projected in more detail. When the first crude telescopes turned toward Mars in the early 1600s, they revealed just enough to tease. White polar caps, like our own. Dark patches that shifted with the seasons. A world that looked from a distance, teasingly Earth-like. Then, in 1877, an Italian astronomer named Giovanni Schiaparelli mapped the surface in detail and described long, straight lines crossing it. He called them canali, the Italian word for channels, meaning simply natural grooves. But when his work crossed into English, that single word was mistranslated into something far more loaded. Canals. And a canal is not a natural feature. A canal is dug. A canal implies engineers. A canal implies a civilization. One mistranslated word lit a fire in the human imagination that took a century to put out. The American astronomer Percival Lowell seized on it completely. He built an entire observatory in the Arizona desert, largely to study Mars, and from what he saw, he constructed a haunting story. An ancient, dying race on a drying world, desperately digging a planet-wide network of canals to carry meltwater from the poles to their parched cities. He wrote books. He gave lectures. He convinced much of the public that Mars was inhabited. He was wrong. Completely wrong. There were no canals. The straight lines were an optical illusion. The human eye and brain straining at the very limit of what those telescopes could resolve, connecting scattered dots and smudges into lines that were never there. Our own minds had drawn the civilization we wanted to find. But here is the thing about that mistake. Even after the canals were disproven, the idea they planted refused to die. The notion that Mars might hold life had taken root too deep, And so, we sent machines to look. The first close look was brutal. In 1965, NASA's Mariner 4 became the first spacecraft to fly past Mars, and it sent back just 22 grainy photographs. The world held its breath and then deflated. The images showed a surface pocked with craters, grey and lifeless, looking far more like the dead moon than a living Earth. And Mariner's instruments delivered the colder blow. The Martian atmosphere was revealed to be shockingly thin, less than 1% as thick as our own. Far too thin for liquid water to survive on the surface today. Water there would freeze or boil away into the near vacuum almost instantly. In a single flyby, the dream of a living Mars seemed to die. The red world was apparently a corpse. Except the story was not over, because we had only seen a sliver of it. 6 years later, in 1971, another spacecraft, Mariner 9, did something no machine had done before. It didn't just fly past Mars, it slipped into orbit and stayed, becoming the first spacecraft ever to circle another planet. It arrived to find Mars completely hidden beneath a planet-wide dust storm, the whole world erased under haze. So it waited, and as the dust slowly settled, a landscape emerged that stunned everyone watching. This was no dull, cratered rock. Mariner 9 revealed Olympus Mons, a volcano so enormous it is nearly 3 times the height of Mount Everest, its base wide enough to cover an entire country. And it revealed Valles Marineris, a canyon system so vast it would stretch across the entire United States, in places plunging several times deeper than the Grand Canyon. Mars, it turned out, was not a dead pebble. It was a real, dramatic, geologically violent world, with the largest volcano and one of the largest canyons in the entire solar system, and a world that demanded a closer question. Not just what does it look like, but is anything alive down there? So we landed and asked directly. In 1976, 2 Viking landers touched down on Mars, the first spacecraft ever to operate on its surface for any length of time, carrying instruments designed to do one thing above all: hunt for life. And what happened next has never been fully settled. One experiment, called the Labeled Release Test, worked like this. The landers scooped up Martian soil, fed it a nutrient broth laced with a traceable marker, and watched to see if anything ate it, if anything metabolized the food and breathed out gas, the way microbes do on Earth. And at both landing sites, thousands of miles apart, the test came back positive. Gas was released, in a pattern that looked strikingly like living metabolism. But another instrument on the same landers, searching for the organic molecules that life is built from, found nothing. And that contradiction split the scientific community down the middle. The lead scientist of that labeled release experiment, a researcher named Gilbert Levin, was convinced to his core that they had found life, and he defended that conclusion for the rest of his life, for over 4 decades, until his death in 2021 at the age of 97. The broader scientific consensus, though, came to a different verdict, that the positive signal was a false alarm, produced not by biology but by strange, reactive chemistry in the Martian soil, most likely those toxic perchlorate salts, which can mimic the signature of life by releasing gas on their own. Most scientists side with the chemistry. Levin never did, and the honest, slightly unsettling truth is this: the debate has never been fully resolved. Even more striking, in the decades since Viking, we have not sent a single dedicated life detection experiment back to Mars. The one time we looked directly for life, the answer was a question mark, and we have not asked again. What we did instead was follow a different clue: water. A fleet of orbiters and rovers, over the following decades, slowly rebuilt the story of Mars's ancient past, and it rewrote everything. Because while Mars is bone dry and frozen today, it did not always look this way. The evidence is now overwhelming and everywhere. Dried up river valleys carved by flowing water, the flat floors of ancient lake beds, and minerals, clays and salts that can only form in the presence of liquid water, scattered across the surface like fingerprints. Billions of years ago, Mars was warmer and it was wet. Rivers ran, lakes pooled, possibly even a shallow ocean. But exactly how wet and how warm is where scientists genuinely disagree. One camp reads the evidence as a Mars that was long and steadily warm and wet, a mild world with stable rivers and lakes, the kind of place where life could take hold and endure. Another camp argues for something colder and harsher, a mostly frozen Mars, icy for long stretches, thawing only in brief occasional bursts before locking back into deep freeze. Warm and welcoming, or cold with fleeting thaws. The rocks have not yet fully decided the matter, and the answer changes everything about whether life ever had time to begin, which is exactly why our two most advanced rovers went where the water once was. NASA's Curiosity rover has spent years exploring Gale Crater, climbing through the layered floor of what was once a lake, reading the chemistry of its ancient mud. And Perseverance now drills into the delta of Jezero Crater, a place where a river once emptied into a lake, laying down sediment in exactly the kind of setting where, on Earth, life leaves its traces. Perseverance is caching those samples now, sealing them in tubes, in the hope that someday they can be brought home and examined. And Curiosity, all the while, keeps stumbling into one of the strangest mysteries on the planet: methane. On Earth, the vast majority of methane in the air is produced by living things, and Curiosity's instruments keep detecting faint whiffs of it near the surface of Gale Crater. Tiny amounts, less than half a part per billion, the equivalent of a pinch of salt dissolved in an Olympic swimming pool, that appear at night, fade by day and occasionally spike far higher for no clear reason. Here is what makes it a genuine mystery, and not just a curiosity. Europe's ExoMars Trace Gas Orbiter, an instrument roughly 1,000 times more sensitive than Curiosity's, sent specifically to sniff out methane from orbit, has looked for years and found none. Nothing. One machine on the ground keeps smelling it. A far sharper machine overhead cannot find a trace. Both cannot easily be right, and no one has fully explained the contradiction. And the source of Curiosity's methane, whatever it is, remains completely unknown. It could be slow geological chemistry deep underground, or it could be something alive, exhaling in the dark beneath the surface. We simply do not know, and the mysteries run deeper still, literally. In 2018, a team using radar aboard a European orbiter reported something extraordinary: a bright reflection beneath the ice of Mars's south pole, about a mile down, which they interpreted as a hidden lake of liquid water, perhaps 12 miles across. A buried lake on Mars would be one of the most promising places in the solar system to look for living things. But, and this is the pattern by now, other scientists pushed back hard. The temperatures down there should be far too cold for liquid water to survive without extreme conditions, and newer analyses suggest the bright radar signal might not be water at all, but frozen clay or salty ice producing the same reflection. Water or a mirage of clay? The argument is still going, unresolved, with careful scientists on both sides. Notice what keeps happening. Every time Mars offers us a hint of life or water, it wraps that hint in genuine, maddening uncertainty. And that uncertainty leads to a problem most people never consider, one that could ruin the entire search before it even begins. Suppose there is life on Mars, some hardy microbe clinging to a pocket of underground water. Finding it would be one of the most profound discoveries in human history. And here is the terrible irony. The very act of going there to look might destroy the answer. because a human being cannot be made clean. Your body, right now, is not just you. You carry with you around 38 trillion bacteria, very roughly as many microbial cells as you have human cells of your own. You are a walking ecosystem, and there is no way to sterilize a living crew. Every astronaut who ever set foot on Mars would carry an invisible cloud of Earth life with them, in their gut, on their skin, in every breath they exhaled. Now think about what that means. We would travel 100 million miles to answer the oldest question: are we alone? And in the very act of arriving, we might contaminate the evidence with our own stowaway microbes. Find life on Mars after a crewed landing, and how could we ever be sure it was Martian and not something we carried there ourselves? Scientists call this problem planetary protection, the careful effort to keep Earth life from contaminating Mars, and, just as seriously, to keep any Martian material from contaminating Earth. And whether our microbes could actually survive and spread on the Martian surface is itself an open question. Likely, many think, but not proven. We may only get one chance to read Mars cleanly, and a human crew is the messiest possible way to read it. And beyond the science lies one final question, older than any rover, that we have barely begun to answer. If we do settle Mars, who owns it? Who rules it? What laws apply 100 million miles from any court on Earth? The one piece of law we have is the Outer Space Treaty, signed back in 1967 at the height of the Cold War. It laid down a noble principle. No nation may claim sovereignty over another world. No one can plant a flag on Mars and declare it theirs. But that treaty was written for a world of governments and rockets. It never imagined a private company, answerable to no nation, building a self-sufficient city on another planet. And that gap opens a legal void nobody has filled. A truly independent Mars colony would exist in a governance vacuum. Who owns the water a company mines from the ice? What laws would a settler live under? And who would enforce them when Earth is 20 minutes away by radio and years away by ship? And perhaps the strangest question of all, what is the legal status of a child born on Mars, a human being who has never touched the Earth and belongs to no nation on it? We have no answers, and the world is already dividing over the attempt. A US-led framework called the Artemis Accords, laying out principles for peaceful exploration, has now been signed by 70 nations. But two of the most powerful spacefaring powers on Earth, China and Russia, have refused to join and are building a rival framework of their own. And that split is not just a legal footnote, it is the opening move of something much larger. Because Mars is no longer the dream of a single agency, patiently waiting its turn. It has become a destination that nations and billionaires are now racing toward, some in cooperation, some in rivalry, all of them pushing to be the ones who get there first. The obsession that began with a red light in the sky and a mistranslated word has become a contest for a world, and to understand where that contest is heading, the machines being built, the fortunes being spent, and the staggering dream of one day making Mars itself bloom, we have to look at the race that is unfolding right now. For most of the space age, getting to Mars was a game only governments could play. Enormous national agencies, moving slowly and carefully, spending public money, terrified of failure, because a single televised explosion could end careers and budgets alike. Every launch had to work, and that fear made everything cautious, expensive, and painfully slow. Then one company changed the rules entirely. SpaceX did something the old space world considered almost reckless. Instead of trying to make each rocket perfect on paper before flying it, they built fast, flew fast, and let their machines blow up, over and over, learning a little more from each fireball. Failure, to them, was not a disaster to be avoided. It was data, and that single shift in philosophy accelerated everything. But philosophy alone does not reach Mars. hardware does, and their hardware quietly accomplished something people had called impossible for 50 years. For the entire history of spaceflight, rockets were used once and thrown away. Picture flying a brand new jetliner across the ocean, then dumping it into the sea on arrival and building another for the trip back. That was rocketry. Staggeringly wasteful and staggeringly expensive. SpaceX's Falcon 9 broke that pattern. Its booster flies to the edge of space, then turns around and lands itself upright on a pad or a ship at sea to be flown again and again. Some have now flown more than 20 times. Look at what that did to the cost of reaching orbit. In the era of the space shuttle, sending a single kilogram to orbit cost somewhere around $54,000, meaning it cost more to launch a bottle of water than the bottle would be worth in solid gold many times over. The reusable Falcon 9 collapsed that to roughly $1,500 a kilogram, a 90% cut. The impossible had quietly become routine. And Starship, the towering vehicle at the center of this whole story, is designed to go further still. It aims to carry over 100 metric tons to orbit at once, the weight of a fully loaded semi-truck, and to be the first machine in history where both stages are fully reusable, nothing thrown away at all. SpaceX's target price, if it all works, is somewhere around $100 to $200 per kilogram, perhaps eventually less. From $54,000 to $1,500 to $100. That is the cost of a wall crumbling, and Starship's entire design rests on one bet we have already seen. It cannot carry enough fuel to fly home from Mars. It has to make that fuel there, from Martian air and ice, the very in situ resource plan whose difficulty we walked through earlier. The rocket and the dead planet are locked together. One does not work without the other. But here we have to be honest about where the dream meets the metal, because Starship, for all its promise, is not a finished machine. It is a violent, ongoing experiment. Across 2025 and into 2026, its test vehicles repeatedly failed, tumbling, breaking apart, erupting into fire over the ocean again and again. Each failure taught something. None of them was yet a rocket ready to cross the solar system, and that gap between a soaring vision and still unproven hardware has already forced a retreat. The uncrewed Mars flight once aimed at this year's window has slipped, pushed back by years, as the company turned its focus first toward the moon and toward the stubborn orbital refueling problem it has not yet solved. The grandest destination in the solar system quietly set aside for now in favor of a nearer one. That is the private empire, but it is not racing alone. While one company iterates in Texas, entire nations are moving in parallel, and one of them is moving fast. In 2021, China's Tianwen-1 mission arrived at Mars and did something only the United States had managed before. It successfully landed a rover named Zhurong on the surface. In a single mission, China joined the tiny club of nations to operate on another world, and they did not stop there. Their next mission, Tianwen-3, is designed to launch in 2028 and to do what no one ever has: collect Martian rock and soil, at least 500 grams of it, about a pound of another planet, and fly it back to Earth by around 2031. And here the story takes a genuinely historic turn. The United States and Europe had their own ambitious plan to return the samples that the Perseverance rover has already been carefully collecting and sealing on the surface. But that program, plagued by ballooning costs, was effectively cancelled when the US Congress cut its funding at the start of 2026. Which means, as things stand right now, China is positioned to become the first nation in history to hold a piece of Mars in a laboratory on Earth. And the club keeps widening. The United Arab Emirates sent its Hope orbiter to study the Martian atmosphere, arriving in 2021. India reached Mars orbit back in 2014 with its Mangalyaan probe, succeeding on its very first attempt, something no nation had done before. Every one of these missions, cooperative or competitive, adds to a shared human understanding of the Red Planet, deeper now than at any point in history. But before any of these nations sends people to Mars, most of them plan to rehearse somewhere closer. The Moon has come back into focus, but it is easy to misunderstand why. It is not a stepping stone to Mars. You do not stop at the Moon on the way. The two are in completely different directions. The Moon is something else, a rehearsal stage. Think of it as a dress rehearsal held close enough to home that a mistake need not be fatal. Through the Artemis program, NASA and its partners plan to test the hardest skills: landing large craft, pulling resources from alien ground, running power systems in a hostile environment on a world just 3 days away. 3 days from rescue, instead of the 7 to 9 months that would separate a Mars crew from any help at all. If something breaks on the Moon, you might still get home. That margin is the whole point. The technologies learned there, the landers, the reactors, the life support, can transfer to Mars. The infrastructure cannot. Every bolt still has to be flown across that vast gulf separately. But the knowledge is real, and there is a hard lesson haunting all of it, written in our own history. We went to the Moon before, 6 times between 1969 and 1972, and then we stopped. The rockets stopped being built, the factories were repurposed, the expertise scattered. Within a few years, a civilization that had walked on another world could no longer get back. The capability did not fade because it became impossible. It faded because we stopped choosing to do it. That is the quiet warning beneath every Mars plan. Momentum, once lost, is brutally hard to rebuild. So what would it actually take to make the journey itself less punishing? To shrink the walls we have spent this whole story climbing. The single biggest prize is speed. Remember what those long months in transit do. The radiation soaking into the body, the bones and muscles wasting, the mind straining in isolation. Shorten the trip, and you shrink all of those threats at once. A faster crossing is a safer crossing in almost every way. And there is a technology that could do it. Nuclear propulsion. Instead of burning chemical fuel, these engines use a small nuclear reactor to superheat propellant and hurl it out the back. 2 to 5 times more efficient than the chemical rockets we use today. In principle, that efficiency could cut the one-way trip to Mars by up to half, carving months off the journey and everything that comes with them. Engineers are actively developing this technology, both the kind that heats propellant directly and the kind that drives it with electricity. But, and it is a real caveat, no such engine has ever flown a crew anywhere. It exists in test stands and design studies, not in space. It is a promise, not yet a ship. There is one more idea for protecting the body, and it is almost elegant in its simplicity. The deepest damage of the journey comes from weightlessness, from the body losing the gravity it was built for. So what if we simply gave it back? Not with some exotic device, but with motion. Spin the ship. Picture a spacecraft rotating steadily as it coasts toward Mars, like a bucket swung in a circle on a rope. The spin presses the crew outward against the floor, mimicking the pull of gravity. Their bones stay loaded. Their hearts keep working. In theory, artificial gravity could erase much of the harm the transit does. In theory, because the physics is unforgiving. To spin comfortably at full Earth gravity without making the crew constantly dizzy, the ship would need a rotating radius of roughly 200 to 300 meters, the length of 2 or 3 football fields laid end to end, turning slowly in the dark. Build it smaller and spin it faster to compensate, and a new problem appears. Every time a crew member turns their head, the mismatched motion triggers waves of disorientation and nausea, an effect that comes from the physics of spinning frames. Too big to build easily, too small to feel right. And so, despite how much it could help, No spacecraft with real artificial gravity has ever been built, and no current funded plan to reach Mars actually includes it. The simplest sounding fix remains for now just a drawing on a page, which brings us, at last, to the most audacious dream of all. Not just visiting Mars, not just surviving on it, transforming it, terraforming. The idea of taking a frozen, poisoned, airless world and slowly turning it into a second Earth with a breathable sky, liquid water, and open air a human could one day walk beneath without a suit. The core plan sounds almost plausible. Mars has carbon dioxide frozen into its polar caps and locked in its soil, the same greenhouse gas warming our own planet. Release enough of it, the thinking goes, and it would thicken the atmosphere and trap the sun's heat, warming the planet in a runaway cascade until the ice melted and the air grew dense. But here the science delivers a sobering verdict. In 2018, planetary scientists Bruce Jakosky and Christopher Edwards, in a NASA-sponsored study, took a careful inventory of every bit of carbon dioxide we could realistically release on Mars, and they found there simply is not enough. Even if we unlocked all of it, every reachable molecule in the ice and rock, it would warm Mars by less than 10 degrees Celsius, under 18 degrees Fahrenheit, on a world whose average temperature sits around 60 below 0 Celsius. That is nowhere close. Most of the gas they found is locked away where we cannot even get to it. Now, the debate has not fully closed. Newer proposals suggest a cleverer approach, not brute force gas, but engineered particles, tiny aerosols scattered into the sky to trap heat far more efficiently. Recent studies suggest that kind of artificial warming might actually be feasible, but warming Mars a little is a long way from making it a breathable second Earth. That fuller dream remains far out of reach, and even if we did warm it and thicken its air, one problem would quietly undo everything. Mars has no global magnetic field, the invisible shield that protects Earth's atmosphere. Without it, the solar wind, the constant stream of particles from the sun, slowly strips a planet's air away into space. It is part of why Mars lost its atmosphere in the first place, billions of years ago. Any new atmosphere we built would face the same slow erosion. Terraforming Mars, if it is possible at all, is not a project for this century or the next. It is a project of many thousands of years, a dream measured in the lifespan of civilizations, not people. So strip away the grandest fantasies, and what actually lies ahead is something quieter and more human, a path taken one careful step at a time. First, more robots, scouting, mapping, searching for water and hazards. Then the rehearsals on the moon, proving the hardest technologies 3 days from home. Then someday, the first crewed landing, and it need not be a colony to matter. Even a single crew spending 30 days on the surface and coming home alive would be one of the most staggering achievements in the history of our species. Then perhaps a small permanent base, and then, slowly, painfully, the long climb toward a settlement that could feed and sustain and repair itself. But notice the fragile thread running through every step. Each phase depends entirely on the one before it surviving. Not just the engineering, but the budgets, the politics, the patience of nations across decades. We already know how easily that thread snaps. We proved it when we walked away from the moon. And even if it holds, even if every rocket flies, every base is built, every step succeeds, one final question waits at the very end of the road, the deepest question of all. Getting a few people to Mars and even keeping them alive for a while is one thing, but a handful of visitors is not a colony. A colony is not a base. A colony is something that lasts, that grows, that raises children, that carries on after the first pioneers are gone. And whether that is even possible, whether human beings could ever truly become a people of Mars, generation after generation, on a world that was never meant for us, is a question that reaches beyond engineering, into biology, into deep time, and into what we are willing to become. The people who go first will not be like us. Not really. They will be among the most extraordinary human beings our species has ever produced, not for their strength or their fame, but for what they are willing to accept. Because to go to Mars in these first generations is to accept a risk that cannot be engineered away. No matter how good the rocket, how thick the shielding, how careful the plan, some danger will always remain. And they will go anyway. They will go knowing the truth of everything we have walked through, knowing that a routine illness could kill them where no surgeon can reach, knowing that the radiation is quietly counting against them with every day in the dark, knowing that the isolation may press on their minds in ways no training can fully prepare them for. They will carry all of that willingly across the void and step out onto a world that would kill them in seconds if their machines ever failed. They are the pioneers, and history will remember their names. But here is the strange truth about pioneers. They are never the ones who truly change everything. That falls to the people who come after, the ones who never chose Mars at all. Because eventually, if a settlement holds, a child will be born on Mars. And that changes the entire meaning of the endeavor. The first colonists will always be visitors at heart, people from Earth adapting to a foreign world, homesick for a blue sky they remember. But a child born on Mars remembers nothing else. To that child, red dust and a pink sky and 1/3 gravity are not strange. They are simply the world. They are home. And that child's body would grow up shaped by a force no human has ever developed under. Remember, Mars pulls with only about 38% of Earth's gravity, barely a third. Every bone that child grows, every beat of their developing heart, every muscle that forms as they learn to walk, would calibrate itself to that gentle pull, not to Earth's, to Mars's. And no one knows what that does to a human being. We have never watched a child develop under partial gravity, not once, not even in an animal. Their skeleton might grow long and delicate. Their heart might form for a world where blood weighs almost nothing. And here is the quiet, staggering consequence. A human being born and raised on Mars might never be able to safely come to Earth at all. Our gravity, the ordinary pull you feel right now, holding you in your chair, could be crushing to a body that never learned to resist it. They could stand on the soil their grandparents were born on and be unable to bear their own weight. Sit with that for a moment. The children of Mars may be the first humans in history for whom Earth is not home, but a hostile foreign planet, a place they can see and long for and never touch. And stretch that forward across not generations but millennia. A population living apart, under a different gravity, a different sky, different pressures on the body and the mind, cut off from the great river of humanity. Over deep enough time, the two branches could drift. Not tomorrow, not in centuries, but eventually isolation is exactly the force that, across the history of life on Earth, has slowly turned one kind of creature into two. The people of Mars might in the end become something quietly, profoundly different from the people of Earth. That is what a colony really is. Not an outpost, not a base with a flag. A colony is a slow accumulation of people, of children, of knowledge, of a way of living, until one day it is no longer an experiment being run from Earth, but a world in its own right. And getting there runs straight into the deepest wall of all. How many people does it actually take to build a world? This is not a romantic question. It is a brutal, mathematical one, and it may be the hardest wall in the entire story, because it is not about technology at all. It is about us. A tiny crew can survive on Mars for a while, kept alive by supplies and rescue from Earth. But that is not a colony. A true colony has to stand on its own, grow all its own food, make all its own air, repair all its own machines, and, crucially, have enough people to have healthy children and their children after them without collapsing into the genetic dead end of a too small family tree. And how many people that takes is a genuinely open question, with answers that vary wildly. One recent study by the French researcher Jean-Marc Salotti calculated that a genuinely self-sufficient Martian colony would need around 110 people, roughly the staff of a small company, carefully organized to cover every essential job. Another team argued the starting number could be as low as 22, about the size of a large extended family, but only, they admitted, if Earth keeps sending supplies, which means it is not truly self-sufficient at all. And when scientists look purely at genetics, at how many people you need to avoid the slow poison of inbreeding across generations, the estimates climb into the hundreds, and conservatively, past 1,000 diverse founders for real, long-term resilience. A few dozen, or a few thousand. That is how uncertain we are about the most basic question of all, how many of us it takes to last. But raw numbers are only half of it, because a working settlement does not just need bodies, it needs minds, a very particular, very fragile web of them. Think about how much invisible expertise holds up your own life. The engineer who understands the water system, the doctor who can perform surgery, the chemist who can fix the machine that makes your air, the farmer who can coax food from difficult ground, the teacher who can pass all of it on to the next generation. On Earth, if you lose one specialist, another is a phone call away. On Mars, each of those people might be the only one of their kind for 100 million miles. And history hands us a genuine warning here. Small, isolated human communities have, again and again, quietly lost hard-won skills over the generations. Technologies and knowledge that took centuries to build simply fading away, because the group grew too small to keep teaching them. Knowledge is not stored in books alone. It lives in people, in hands, in practice, and it can vanish. Now imagine that on Mars, a single accident takes the one person who truly understands the reactor, or the one surgeon, or the one engineer who knows how the oxygen plant actually works, deep down. In a settlement that small, the loss of one irreplaceable mind could unravel the whole thing, not with an explosion, but with a slow, spreading failure that no one left alive knows how to stop. To get past all of this, to reach a colony robust enough to survive its own fragility, would take three things at once. Launches cheap enough to send thousands of tons of people and equipment, construction fast enough to build a real settlement in years, not centuries, and a sustained human will across decades that never wavers and never gets cancelled. That enabling architecture, cheap, fast and unwavering, does not yet exist, not one piece of it fully. And so we arrive, at last, at the honest accounting. Let's be clear-eyed about exactly where we stand right now. Not hopeful, not despairing, just honest. We have no proven way to land the mass of a crewed mission on Mars. We have never done it, not once, not in a test. We have no verified way to make fuel, air and water on the Martian surface at the scale needed to keep a crew alive and bring them home. We have made oxygen the size of a dog's breath. We have not built the factory. We have no demonstrated way to keep a human body and mind healthy across the full length of the journey. The bones, the blood, the eyes, the radiation, the isolation all still unsolved. And we have never run a fully closed life support system, one that recycles everything endlessly, losing nothing, for years at the scale a Mars crew would need. Not on Earth, not in orbit, nowhere. Now hear this clearly, because it matters. These are gaps in demonstrated capability. They are not gaps in ambition or intelligence or courage. Every single one of them is a problem being worked on right now by brilliant people who believe it can be solved. And this is precision, not pessimism. Naming what is unsolved is not the same as saying it is impossible. Apollo faced a list of impossibilities just as long, a list of things no one had ever done, and many said could never be done. And then, one by one, they did them. The difference between an impossible dream and an engineering problem is often just time, money, and will. So let's come back, quietly now, to the question we started with. After everything, why haven't we gone? Here is the answer finally in full. What stops us was never one thing. It was never a single missing invention, one great wall we could tear down and finally walk through. That is what makes Mars so uniquely, staggeringly hard. It is every wall at once, the distance and the fuel, the fragile body, the impossible landing, the dead world that gives nothing, the silence, the mind, the generations, and behind all of it, always the same cold fact that out there no one is coming to help. Solve any one of these walls, and the others are still standing, exactly as tall as before. There is no single breakthrough that swings the door open. To reach Mars, truly reach it, and stay, a dozen hard-won advances must all arrive, and align, and hold together at the same time. Engines and medicine and reactors and life support and shelter and the fragile human heart, all of it, ready at once. That is a brutal thing to ask of any species. And yet, and this is the part that should not be lost in all the difficulty, every single one of those threads is advancing. Right now, the rockets are flying and landing, the reactors are being tested, the oxygen is being pulled from alien air, the medicine, the shielding, the recycling, the understanding of our own fragile bodies. Every one of them is further along tonight than it was a decade ago. None of the walls has fallen, but none of them is standing quite as tall as it once did either. We are not there. We may not be there for a long time, but we are, unmistakably, on the way. And so, let's end where all of this has been quietly heading, not with a statistic, but with an image. One day, perhaps not in our lifetimes, but one day, the walls will align. A ship will cross the dark and survive the fall, and a human being will step out onto red soil that no living thing has ever touched. They will stand there in a thin and alien wind on a world that our species spent thousands of years dreaming of and dying to reach. And at some point, that person will do the most human thing imaginable. They will stop and they will turn around and look up and search the strange sky for home. They will find it easily, because from the surface of Mars, Earth is not a globe and not a memory. It is a single point of light, a pale bluish star, brighter than the others, hanging quietly in the black. Our robots have already photographed it from there. Everything we are, everyone we have ever loved, every war and every symphony and every ordinary Tuesday, compressed into one dot you could cover with the tip of a gloved finger. The astronomer Carl Sagan once looked at a photograph of that same pale dot, taken from far out in space, and understood what it meant, that everything we know, everything we have ever been, is held on a fragile mote of dust suspended in a sunbeam. He was looking at it from the outside, imagining the distance. But the person standing on Mars would not be imagining it. They would be living it. For the first time in the history of our species, a human being would look at the Earth and see it, truly, from another world, and finally understand, all the way down, what those three small words have always meant: far from home. And in that moment, all the walls and all the numbers and all the impossible engineering would fall away. What would remain is the oldest thing about us, the same restless spark that carried the first humans out of Africa, across oceans, onto every continent, and finally off the planet entirely, now standing on red soil, looking back at a blue star, and quietly deciding that home is wherever we choose to build it next. That is what is really stopping us. Not that it is impossible, but that it is the hardest thing we have ever tried to do, and we are slowly, patiently, one wall at a time, learning how to do it anyway. For 8 walls, we have talked about how nearly impossible it is to leave this world, how much it would cost a human body, a human mind, a human heart, just to stand somewhere else. And somewhere down that long road, someone will. They'll stand on cold red ground, under a small and distant sun, and they'll turn to look for home. They'll find it as a single point of light, a pale, quiet dot, easy to miss among the stars. And in that moment, they will understand something you can feel tonight without ever leaving your chair. That dot is everything, every ocean, every morning, every person you have ever loved, and everyone you haven't met yet. The air you're breathing right now without thinking about it. All of it gathered on one small world that asks nothing of you in return. We spend so long dreaming of how to get there, and the whole journey, quietly, has been teaching us how rare it is to be here. You are already standing on the thing the whole universe makes so hard to reach. Thank you for walking this long road with me, all the way to the edge of another world and back. If it moves something in you, a like and a subscribe tell me to keep going. Quieter journeys are coming, stranger ones too. Look up tomorrow and know how far you already are from anywhere else. Sleep well tonight. You're already home.